Okay, OChem 1, there was one mechanism that we didn't get to do together last night, and I wanted to demonstrate that mechanism one more time for you guys because some of this material can come across really confusing, and the expectations of when to show what pieces of information can also feel very confusing. This reaction is both regiospecific, the halogen and the solvent add to specific carbons of the alkene, halogen to the less substituted carbon, solvent to the more substituted carbon. It's also stereospecific. This is an anti-addition mechanism. When we're given a specific stereoisomer, this one also forms with its um, with the OH dashed and the bromine wedged. Um, when you're given a specific stereoisomer, similar to the top right problem, we want to try and show the mechanism for this stereoisomer. Our first step in the haloether and the halohydrin steps mechanisms is the same step as in the halogenation mechanism. The halogen will react with the alkene. And just like we said before in all of our other mechanisms, we should always be attacking the most substituted carbon. In fact, some of you may see on active that if your mechanism does not show an attack at the more substituted carbon, it marks you as incomplete. So you always want your arrows to be attacking the more substituted carbon, which means attacking from the less substituted carbon. That agrees with our partial charges that we predicted on alkenes. So whichever bromine attacks is the same bromine that is attacked by the alkene, and the other bromide breaks off as a halide. In many cases, it doesn't matter whether you show this halonium ring forming on the top face with wedges or on the bottom face with dashes. But because we're aiming for this specific stereoisomer, I want my halogen to be on the bottom face. When we did this mechanism, we saw that you could draw either version with a wedged chlorine halonium ring, the wedged chloronium ring, or the dashed chloronium ring. Then it just depends on which carbon the other chloride attacks. Let me clarify that. I could have shown the intermediate for this top reaction as a wedged chloronium ring or as a dashed chloronium ring. The difference is to get to this isomer, the chloride would attack at the bottom carbon if the halonium ring is wedged, or the chloride would attack at the top carbon if the halonium ring is dashed. That means that this chlorine stays dashed, or this chlorine becomes dashed. So I preserve the stereochemistry I'm looking for. Here I don't have two choices because there's only one halogen. I need that halogen to be on the bottom face. I need it to be dashed. So I have to show this as a dashed halonium ring. Now my water comes into play. We form a bromide ion, but this bromide ion will not react because there's more solvent that can act as a nucleophile. We always attack the more substituted carbon. So water attacks the tertiary carbon and breaks the CBr bond back to bromine. It's also important that you always break the bond from the carbon you're attacking. It's often that I see students attack one carbon but break the bond of the other carbon, which means this carbon breaks its octet and this carbon loses its octet. Just like in our haloether mechanism that we did together, this gives us a protonated new group that then needs to be deprotonated. You can see that I'm expanding all of my bonds so that you can see why it has a positive charge, and remember that one of these bonds needs to break. Bromide can act as a conjugate base and deprotonate to give me the final product. One student last night asked, how is it that we could alternatively show a molecule of water acting as the base here instead of bromide? This is a fair question because over the reaction arrows, we would only see written Br2 and H2O. Where could I get a second molecule of H2O from? And this is where what's written on paper deviates from what's happening in reality. This is a solvent, so it's present to an extreme excess. I'm only showing one molecule of water throughout, but if I wanted to have two molecules of water play a role in my mechanism, I could just show two molecules of water. Here's our final product. There is another stereoisomer formed. We don't see it shown here, so we're only aiming to form this one. Keep reviewing, and remember, do not invent the wheel. Do not reinvent the wheel. Follow the steps of the mechanism, show every intermediate as it forms. Don't try to have reagents in one step, attacking reagents in another step. These arrows separate our instances of the reaction. This is one instance. This is another instance. This is another instance. The three big takeaways. Attack more substituted carbon. Bonds break toward the partial negative atom, and bonds form from the partial negative atom. I want to highlight this one right here because some people will say that in this step, how can the bond break towards oxygen if it has a partial charge, a formal positive charge? It is still the more negative atom of the two atoms. Oxygen is more electronegative than hydrogen, which means in this bond there is a dipole towards oxygen. Just because oxygen has a positive charge doesn't mean that it's not the more negative. Similarly, in the halonium ring, bromine has the formal positive charge, but it is the more electronegative of the two between carbon and bromine, so the bond breaks towards the bromine. These rules will always be true when doing these types of reactions. Happy studying.